In the first part of this example, we're told that a car is traveling with a velocity of 25 meters per second. The driver suddenly slams on the brakes, and it takes 2.1 seconds for the car to stop. The question is, what's the acceleration? Well, equation 1.3 relates these quantities. It says that acceleration is the change in velocity over the change in time. To use this equation, then, we need to know the change in velocity. What's the change in velocity? Well, the car started out traveling 25 meters per second and eventually comes to a halt. So the initial velocity is 25 meters per second and the final velocity is 0. To get the change in velocity, we simply take the final velocity and we subtract the initial velocity. So delta V equals V final minus V initial. V final is 0 meters per second, V initial is 25 meters per second. So delta V is 0 meters per second minus 25 meters per second, or negative 25 meters per second. Okay, that's delta V. Delta T is easy. It took 2.1 seconds for this thing to stop, so delta T is 2.1 seconds. So now we have delta V and delta T. We can plug into our equation. Remember, the equation says that acceleration is delta V over delta T. So acceleration is negative 25 meters per second divided by 2.1 seconds. When we divide these numbers out, we get negative 12 meters per second squared. What does that negative mean? It denotes direction. I gave the velocity as 25 meters per second. That implicitly defines the direction the car is moving as the positive direction. Well, the acceleration is negative 12 meters per second because the acceleration is in the opposite direction. If the car is going to slow down, then the acceleration has to be opposed to the velocity. So that negative means the acceleration is pointed opposite the velocity. All right, well, let's move on to the second part of the example. In that part of the example, we're told that a ball is falling, and we're told the acceleration is 9.8 meters per second squared down. The initial velocity of the ball is 0. The final velocity is 11.0 meters per second, and the question is, what's the time? Well, once again, to solve this problem, we're going to use equation 1.3. Acceleration is delta V over delta T. What's delta V? Well, it's V final, 11.0 meters per second, minus V initial, 0. So delta V is 11.0 meters per second. The acceleration is 9.8 meters per second squared. So we can put those both into the equation. All right, now all we have to do is solve for delta T. If we multiply both sides of the equation with delta T, then it will disappear on the right-hand side of the equation and reappear on the left-hand side of the equation. If we divide both sides by 9.8 meters per second squared, that will disappear on the left and appear on the right. In other words, we swap the two. Once the two are swapped, we have delta T equals 11.0 meters per second divided by 9.8 meters per second squared. The unit meter cancels. Also, one of the seconds cancel. The second on the top cancels completely, and the squared exponent on the second on the bottom also cancels. So in the end, we have 1.1 seconds. Now we're limited to two significant figures here because of the 9.8. So we know the ball took 1.1 seconds to reach a final velocity of 11.0 meters per second.